Good day. In today's video, we'll look at measuring residual phase noise. So I have here the E5058A SSAX. Let's look at the hardware connections before we move into the software applications. So this is the SSAX. If you notice, this is source 1 and source 2 of the SSAX. Source 1 is just connected directly into RF input 1. Source 2 goes into the input of a preamp that I have here today. This would be my device under test, and the output of that is fed into RF input 2. So now we're back into the SSAX. We will first go into measurement class, and just ensure you're in phase noise. Hit OK. Now we'll go back into phase noise setup. If you've watched the absolute phase noise measurement, you will know the noise type is phase noise, but we're doing residual phase noise in this video, so we'll click that. I will have to change the carrier frequency with the device under test operating frequency. So the preamp that I have starts from 2 GHz. I will change this to 5 GHz. And I would like to just bunk the offsets down to 1 Hz as well. Let's do that. I'll reduce the RBW to 3, and I'll just keep the cross correlation factor at 1. Now for residual, we'll just have to look at the RF path. There are some things to take note here. So I only have 1 device under test, so I'll keep that as 1. If you do have 2, this is what it will look like if you're trying to compare the phase noises using cross correlations and reduce the noises you get out of the source. But I only have 1, so that's how I have connected. So if you remember from my hardware connection, I had the internal source. You also have the option to use external, but that's not what we're doing in this video. And have source 1 out to RF1 input. Source 2 goes into the DOT input port, and the output port of the device under test is fed into the RF2 input. So I have to make sure this is correct, and it is. If you do have delays that you like to add in, you can go into path delay compensation and measure at your path delay. I'm not doing that, so I'll just cancel that. Now we would have to go into the source. By default, this is off. We would turn this on, and we have said we would set this at 5 GHz. That's what I'll do. I just want to make sure my device will be powered up, so I'll put in 5 dBm. That's about normal. I will leave spurious out. I don't plan to put integrated noise. And hit apply. So now if I hit OK, we can see it's still sweeping. I will do a single measurement instead of running continuous. And if we give it a bit of time, it should then show me the phase noise of my device under test with cross correlation method. So as you can see, out of the source 1 is 3.3. I do have about 12 dBm out of the device under test, and that's about right, as my output power of the amp is about 8 dBm. And as you can see, I do have the phase noise of device under test, which is looking decent here. You can change up the X correlation factor if you like. Let's turn this to 5 and hit apply, just for measurement wise. I might want to auto scale this a bit so it looks a little more viewable. And we'll be right back as we get closer to the measurements. So we're getting close for the measurements to be completed. And there you see the resolution's a little better. Again, if you go into phase noise setup and turn on spurious table, it would show a few spikes that it was detected, spurs that it was detected. If you do not enable the spur analysis, then you do not see any of spurs. So this is how you can do residual phase noise measurements, where you try to remove the contribution coming from the internal sources. And of course, there are a few factors here that would affect your measurement, and mainly that would be RBW ratio as well as the cross correlation factor. So just bear in mind that the cross-correlation factor will improve or provide additional accuracy, but it will take extra time for your measurement to be completed. So that's all for today's video. Thanks for watching.